Okay, are you ready to get started? Okay, our next speaker was gracious enough to give up some of his time so Lawrence Lessig's talk could go on. But it's time we get started because we're running a little short on time. Our next speaker is Luis Moraz. He has about 10 years of security experience and about 5 years doing reverse engineering of hardware and software. His presentation is on automated exploit detection in binaries. So please give a warm welcome to Luis Moraz.
Thank you. It was supposed to be 2 people to this talk. Matt Hargett is the other person that I'm working on this project with. He actually couldn't make it, but he wanted to say hi, and sorry he couldn't make it. And maybe he'll show up next time. But this talk's on automating exploit detection, or really looking for vulnerabilities in binaries by doing static analysis. There's been some work in this field. A lot of stuff is going on right now with source, looking through source for vulnerabilities automated. But this talk is going to deal exclusively with binaries, the types of problems that you run into trying to emulate and trying to predict branches and stuff like that, and what can be done and what can't be done. I'm not going to come up here and say that it's going to catch all the vulnerabilities and it's going to be, it's just going to drop ODay at you. It's not. It's going to catch some vulnerabilities, and then it's going to speed up audits, and it's going to get rid of a lot of low-hanging fruit and whatnot. More complicated vulnerabilities, that multi-step things, things where you're exploiting probably 2 or 3 vulnerabilities at the same time to be able to execute your code. Things like that, I don't know. Maybe it'll catch part of it, maybe it won't. That's a lot of why I'm working on this project. It's really interesting, and I want to see where it goes. So I'm going to talk a little bit about the definition, like some of our definitions, what the architecture is, and some of the challenges and the problems that come about doing this type of work. So the project is called Bug Report. It's on SourceForge right now. It's by no means a product or a real-world tool yet. It's just proof of concept code. We keep on working on enhancement as issues come up. And as I get into the architecture, really all it's going to be is going to be an emulator and some analysis on top of an emulator. And thanks. So it's all written in C#. This is actually the first time that I use C#. I wanted to use a language that ran in a sandbox, was able to run in Linux and in Windows. So everything that we're using runs in mono. We're not using any Windows forms or anything like that. It's all command line. The tool is released under GPL v3, the latest draft, which is 2. And some of the other reasons we use C# is it's very similar to C++. Most of my development has been in really assembly and C, and so this is and a little C++. So it's kind of cool to learn a new language, and it was also nice that since it was sandboxed, we can use a lot of the built-in exceptions to catch some of the overflows. So we'd use stuff like create buffers to emulate the stacker and whatnot. And if there was, if we're writing past a certain location when we emulate an opcode, then the .NET catches it and throws an exception, and we trigger on that exception. So targets of detection. A lot of vendors have their own definition of what an exploitable bug actually is. If you talk to a vendor, sometimes they'll say, like, depends what you mean by exploit, depends what you mean by bug. Because they're trying to up their numbers and say that, they catch this or they catch that. All we're looking for, our definition right now, is an out-of-bounds memory write using user-supplied data, tainted data. Doing out-of-bound reads can be vulnerabilities. Let's say you're able to read password files, hashes, variables, other types of logic from memory. That's definitely a vulnerability, but right now we're just concentrating on writes. And you can also, at times, maybe do an out-of-bound write without tainted data, like you terminate a null, and that causes, let's say, a heap overflow, and it changes the lowest byte. You could do things like that, but all we're doing right now is tainted data. It's the easiest thing to trace through, and I'll show you how it works. So we have, part of our tool comes with a lot of system tests. The whole tool was written with using like test-driven development, so we have lots of unit tests within the tool to test the functionality, and then we have system tests, which are really just simple C programs that have something comes in from argv, you malloc like 16 bytes, and then you write to position 16 in the buffer, so you write one past the end of the buffer, stuff like that. And then we trigger on stuff like that, and then we keep on cycling through tests. So every time we add a feature, we make sure that everything that we've done in the past still passes. Looking at some other vendors' products and whatnot, at times they'll issue an update, and things that they used to catch, they won't catch. Things that they didn't catch, they catch now, so there's no way of controlling quality. So this is one reason that we did it this way. So this is the architecture. Basically, it's a set of tests that is part of the project. They're all on the part of this version tree, so you can check those out and see how they work. Then there's a core x86 emulator that's separate from the analysis engine, because we want to be able to do, let's say, ARM later on and different processors. So we're really trying to modularize it so that analysis and the processor-specific code is separate from each other. So these are some of the challenges, some of the problems that you encounter when you're doing this type of binary static analysis. One is branches. When do you take a branch? When do you not take a branch? You don't know all the data that's coming into your program. So certain decisions have to be made about what kind of state comes into the branches, what kind of state leaves. Something else that's really important is inner function analysis. No longer are we going to have a single function going to be the vulnerability and everything is there. The only time that happens is like sample programs that show you how buffer overflow works. Nowadays, you're going to have data coming in from a user somewhere else, and then it gets fed up a call chain, and then the vulnerable function is way somewhere else. Something else that has proven a little difficult sometimes is non-continuous functions. Most new compilers, like I think SP2 was all compiled with 7.1, which is Visual Studio 2003, that has non-contiguous functions, and everything from there on does. If you do a lot of reversing of Microsoft stuff or patches, you'll notice it, lots of non-contiguous functions. Something else that can be a problem is self-modifying code, which, I don't know, we don't really care about, because we're looking for vulnerabilities in vendor software, and I don't know any vendors that I want to own that use packers or, self-modifying code. Usually is just straight code. And something else that can be a challenge is loops. Loops sometimes can be difficult because it requires a little bit of like an algorithm to analyze if it's going to overflow something, if it's a bounded loop, if it's an unbounded loop. And something that we've done specifically for this project is we've taken different compilers, we've taken different optimization levels, and we run each test through each of these levels. Because you don't know like what switches different vendors are going to run in. So we're trying to really make it generic so we can tell what's going on and not have not rely on, let's say, one version of a compiler or certain sets of switches. Some other vendors have done things like that, and it doesn't really work very well. So dealing with branches. There's two possibilities. You have a known value. If you have a known value, it's easy. Let's say you're comparing, there's going to be a 0 coming into a basic block, and you're comparing EAX is 0 and you're comparing it to 0, you know what's going to happen. One machine state is going to come out of that. If you have unknown values, you don't know what EAX is, you don't know what's being passed to that function. It's coming off the network or whatnot. It's part of a buffer coming off a network. It could be anything. Then you're going to have, for every compare before a branch, you're going to have 2 machine states. And you have to decide, what are you going to do? Are you going to follow one path? Are you going to follow another path? Are you going to follow all the paths? This can become problematic as things start to explode out on how many different combinations there are. So one thing that we're using is constraints. Constraints is a way to say a certain unknown value has a certain range based on calculations that were performed to reach that level. So if you did a comparison earlier and it said there was a branch and let's say it said less than 5, and then you see another comparison and it says greater than 8, you know it's not going to be greater than 8 because you got there through less than 5. So things like that. I have code examples that'll show that a little more clearly, but constraints is basically a way of being able to have a range of unknown values without actually knowing exactly what it is. So when you're dealing with branches, the jumps, the SVBs, all that, don't really decide what happens based on input. Those are all reactions based on the compares, the test, math instructions, and whatnot. Those set flags, those are the things that cause the different machine states to appear, the different combinations. And the jump, the like J and E, whatever, because this is all x86, so that's what I'm using right now, is all based on the comparisons and the flag conditions. So branches really come down to comparisons and the results of comparisons. So here's a little bit of like pseudo assembly. So in line 1, we compare EAX with 0, and if it's not 0, in line 2, it's going to jump to 4. So line 4. So coming into this, if we get to line 4, we already know that EAX is constrained. EAX cannot be 0. So we already know certain things about EAX. And you start doing these type of things, and you start gaining more knowledge about what values can be through certain paths. And all these different paths each basic block describes a transformation or a path that it goes through. There's an input state into a basic block, and there's an output state. And you start combining these things together, as we'll see later, and functions basically are just that. They're basic blocks, which are transformations of input and output strung together into a big expression. So how do you choose branches? You could cheat. You could follow all branches and see what happens. See, it's going to take you down a certain code path. You're going to be able to analyze part of the program. You're going to have some code coverage. Something else you can do is randomly pick branches. That'll probably give you more code coverage. You'll go through more of the code. You can also take every branch. So every time you hit a comparison or a branch, you take both sides. Eventually, this is going to get really big. It expands and expands and expands. Real software is going to have tons and tons of branches. So option 4 is to take some branches. So somehow decide which ones you're going to take based on certain constraints or certain things that you want to test. You want to test maybe really small values, really large values. Maybe you want to test -1. Maybe you want to test 260, which is like the max path in Windows, or maybe 259, which is one less. So you can try to limit it based on knowledge that you've acquired from other vulnerabilities. So in choosing branches, a lot of functions are going to have guards at the beginning. Like, let's say you're passing in a pointer. It's going to check if it's null right at the beginning, and if it is, it's going to return right away. So usually in the assembly, guards are going to drop through. And if it passes the guard, it's going to jump over the return. So taking all branches is usually going to give you way more coverage than taking none of the branches, because you'll probably hit all guards and return and nothing will happen. So here's an example of just a little bit of C. If there's less than 2 arguments, you exit, and if not, you print 23C3. So if we take a quick look at this in assembly, I've edited out the instructions that don't really apply to the logic, like stack manipulation and whatnot. So in the first line, you're comparing argc with 1, and it says if it's jump then greater, then you're going to jump past the guard. So if it's 2 and above, it's going to jump past the guard. And if it isn't, it pushes -1, which is all Fs, onto the stack, and then it calls exit. So here's an example of a guard in assembly where the failure of the guard drops through, and taking the branch is going to get you to the rest of the code. So that's one way that people have done stuff, and you're going to find some stuff that way. Another way to choose branches, there was a tool called Prefix, and it randomly took branches. Microsoft bought this tool, I think around maybe 2000, if I'm not mistaken. It was bought by Microsoft and it was shelved. Lots of people still run this tool because you can't get it anymore. They're not releasing it, and basically it just picks random branches and it goes through. There's some problems with it that you're not going to duplicate your results, right? You're going to run it through, and maybe you'll find something. You run it through the next day, and it's not going to find it or find something completely different. I think beginning with the DDK for maybe 2003, I'm not sure, Prefast came out. Prefast is basically like a neutered version of Prefix. It doesn't do inner function value tracking. It only works in the function. That's not really that useful. So yeah, I've talked to lots of people that still have their prefix, and they love it, and they're not partying with it for anything. So you can take all branches. If you take all branches, you're going to have multiple machine states. And when you take a branch, by the definition of taking a branch, you've set a constraint on the input. If you take a branch and it's, the comparison is this greater than 5, you have to find that the path is going to be greater than 5 for that value. Something else that you need to make sure is that you don't break these constraints later on. If you've taken a path that says it's greater than 5, damn. I'm taking donations. Anyone else want to bring a beer? Just feel free. So you have to just make sure that you don't break your constraints. If you take a path and you say like EAX is greater than 5, don't invalidate it by taking another branch that's going to betray that constraint, because that'll never happen in real life. So here's a little function. This has it's being passed a character pointer, and there's some comparisons done on it. And there's going to be multiple machine states coming out of this. Sorry for how messy it is, but it's really hard to put code on here and allow people to read it. But basically, the first if is checking if x is not equal to 0, and then it goes into that inner comparison. And if it is 0, then it's going to subtract 1 from the size. Within the inner comparison, it's checking if it's not a new line. And it does something with a size. Otherwise, it also does something different with the size. So what are all the potential states? Well, the first state is that x is less than or equal to -1, or x is greater than or equal to -1, meaning that x is not 0. It's also that x is not equal to a new line, and that would make size equal to 2. That's taking the first block and then taking the else. Taking the first block and taking the first if, and that being true. So the next possibility is that x is equal to a new line, and that would make size equal to 3. That's if it takes the first if and it takes the second, the else within that block. And the last possibility is if it just drops straight through the outside else, and it just subtracts 1 from size. So we know that x equals 0 and size equals 0. So real code is going to have way more potential states than this. I mean, this is just a simple function. But this is kind of how you create constraints. And later on, when you call other functions and stuff, there's possibilities that these constraints are going to merge, and this explosion can kind of trim down. And that's really what you're looking for. You're trying to minimize the possibilities. Another thing that you can do with this is if you have multiple states, like I said before, maybe there's certain values that you really want to look for. You want to check for negative numbers. You want to check for certain constants, like in windows.h if you're doing Windows stuff, or whatever, or other things that have had known problems, like you could try a -1, -4, things like that. So going on to inner function tracking, there's basically 2 types of approaches. There's top-down and there's bottom-up. So top-down, you look for an export. Let's say there's a DLL. You're going to start at all the exported functions. Or let's say it's just a regular program. You're going to go into main. And you're going to start there. And you start traversing through all the functions. Just like if you're reading code. You start at the beginning. You go through. You take all the function calls. You analyze all that data. And you basically you weave your way all the way down, back up, and go through the whole tree. Here's some sort of pseudocode. All I did was list the function calls. There's other things probably going on in there. So you need to know what these functions do to be able to figure out what the next function up would calculate or perform. So it's not just function calls, but I just listed the function calls because there's not enough room on there to list real code, or else no one can read it. So here's a little graph. This is going to be like the function call graph. On the left-hand side, you have the name of every function, how many times it goes through, and we're going to step through top-down analysis. So first, we're going to start off in main. And in main, we're going to see we have these 3 different calls. So we go here to foo. That's going to call x, that calls y, that calls z. X calls z again. Main calls x, x calls y calls z, and x calls z again. And then again for bar now. So this takes a really long time. Complexity can really explode. This is only this is a really small function. I mean, this is a really small program. And as you notice, z got hit 5 times. A lot of these functions are being hit multiple times. So it's really time consuming. We're hitting functions multiple times. Z was hit 5 times. A lot of times, what Matt, he's the one that works on this project with me, kind of defines as that, is kind of like taking a yo-yo and throwing it down the Grand Canyon, and you just wait there for a little bit. It's going to take a long time, and then it comes back up. So every time that you go down these paths, you have to do it again, and it comes back up, and again. So this is very CPU intensive, very time consuming. So the other solution is bottom up. And in this, you try to describe each function in isolation. You're going to taint the return values. And you try to store an expression or some type of constraints for a transformation. So whatever input you have, based on constraints, if this is less than this is what this function is going to do. If it's greater than this is what this function is going to do. And you try to keep that cached. So what you're really trying to do is create like a diff. You have a machine state. A machine state is like your registers. Even your stack is part of your registers, because ESP, EBP points to your stack. I mean, your stack gets pointed to by these registers, and everything is controlled through there. So if you have this machine state and you can define your function as a transformation of this machine state where you have input and output, kind of like a black box, but you have this expression. This is what bottom up is all about. So it works well for deeply nested calls. You're basically tainting all the return values, but it's going to require multiple sweeps. So this is the same code. And the first pass, this is a little bit different. The first pass, what we do is we start in main, and we look at all the function calls in main. And if the function calls if they're calling something else, if they're not solved, none of these are solved. We don't know what foo does exactly. We don't know what x does. We don't know what bar does. So none of them are done. We don't have any information about this, so we have to move on. Then we go to foo. This calls x. We still don't know what x is or what x does, so we move on. Same thing with bar. It calls y. We haven't solved y. Y calls z. We haven't solved z yet. And x calls y and z. So there's this pattern. If we haven't solved it, we keep on moving down the tree. Finally, z returns something. It's the leaf node. It doesn't call anything else. So we have an idea of, based on some kind of input, what the return is going to be, and we create this expression. Z is now solved, so we can cache z. We can cache this expression for z. So that was one path down, and it seems a lot like top down, but the difference is that z is done. Z is evaluated as a diff, and the analysis is cached. You don't have to look at z ever again. Instead of before, where you have to go down like with a yo-yo, and you have to go down the call chain and come back up and analyze everything over and over again. You have a definition for z, and it's cached, and you don't have to do that again and again. So here we start on the second pass. We start the same way. We're in main. Foo, x, and bar are not solved, so we have to move on. Again, foo calls x. We don't know what x is. Bar calls y. We don't know what y is. X calls y and z. We know what z is, so we don't have to analyze z again. We have the answer for that already. And we don't know what y is. Once we move into looking at the y function, since we know what z is and it's cached, we have all that information already. We can pass that up, and now we can create an expression for y. So now we've solved two functions within this program. So at pass 2, we have z and y cached. Every time you do the sweep or this pass, you're going to get more and more functions. So I'm not going to step through it again and again, but so after the third pass, this is what you're going to get. After the fourth pass, you solve all this, and after the fifth pass, this is what you have. And this again also, went through multiple iterations, and it's not the most efficient way to do it. It took 5 passes. So this is called bottom up because you solve all the functions at the bottom, and it kind of bubbles up like it's boiling. All your information starts coming up, and as you keep on analyzing it, it keeps on coming up to the top. So some optimizations is you can, let's say you disassemble the whole program. You look at leaf nodes first, because leaf nodes don't call anything else, so this can be solved. So you solve off the leaf nodes. Then let's say you look for functions with low amount of calls. So you look for functions that call maybe one other function, call a leaf node, right? And have lots of cross-references. So you set those on a higher priority, because if it has lots of cross-references, that's going to reach up to more functions. So ideally, what you're really trying to do is combine both these approaches. Both these are different academic approaches. Some people are like, it's top-down or nothing. Some people are like bottom-up or nothing. What we found is the best is kind of like a hybrid of both. It's going to get you the most code coverage with the fastest time. So non-contiguous functions. I don't really see these as a problem for anything. They were a little confusing at first when they first came out to do reversing, but if you look at them, they're just basic blocks. It's just input and output. It doesn't matter if it's in the same continuous address space. It's doing the same type of thing. So, the only reason we have functions is because that's how we program. We all a function is a single entry point and multiple exits, right? Basic blocks are one entry point and one exit point. The difference between a basic block and a function is there's some stack effects, right? When you go into a function, you have to manipulate the stack, your return address. When you exit a function, the way you calculate where you're going is also based on the stack. But there's really no difference between basic blocks and functions. It's the only reason we have functions is because that's how we code in C or C++ or whatever. The machine doesn't care. You could have tons of basic blocks and jump in between them. It doesn't really matter. So for like automated analysis, a function or basic blocks, a function has more cross references. A function exits a little bit different, but it doesn't really matter. So a basic block, since it has one input and one output, is kind of like, you can think of it as a math function. You have one thing goes in and one thing goes out, and there's like some type of transformation. So you take all these transformations, all these expressions from basic blocks, and you string them together, and that's your function. So that's kind of how we try to come up with these expressions and transformations to define functions, so that when we do the bottom up, we have like a formula for it. We don't have to analyze it all over again. And like I said, I don't care about self-modifying code. No, I don't care about analyzing worms or whatever for vulnerabilities. I care about owning Microsoft. I care about Oracle. I care about the good stuff. So I'm going to show unbounded loops next. I'm going to cover my friend Matt, that's part of this project. He used to work doing static analysis. He had his own company, and then he sold it. One of the bugs he found was a client-side vulnerability in Trillian in the RSS reader. And it's basically one of these unbounded loops. This is also very similar to what we saw with the MSRPC DCOM, like the blaster worm, where there was an unbounded loop looking for a backslash on the computer name. So this is what we use to find loops. We find something that's closed on itself, and there's a pointer. This pointer is being used for two things. It's being used to write out a value, and it's also being incremented. The exit from the loop is tainted byte comparison. So there's some user input involved in it. We track all tainted data, so we know if it's tainted or not. And that comparison that was used is being written to this pointer. So we know that user data is being written out to some location, it's being incremented, and that defines an unbounded loop. This is like an inline stir copy. Lots of compilers will do this instead of calling a library function. You save having to write stuff out onto the stack. You save having to do return, like all kinds of stuff. So this is an unbounded loop. It writes from the source to the destination. And once source is null or 0, then the expression is going to be 0, and it's going to exit from the while loop. So let me show you the Trillian vulnerability in IDA. So here's the entry to the loop. That's the top where it comes in. What it's doing here is there's a receive call. It's reading 1 byte at a time. This AL is the buffer is being held in. It's really hard to read sideways, but the buffer holds the 1 byte. It's being written to AL. Then AL is writing it to this combination of a base and an index pointer. EDI is going to be the base register, So that's the address of the buffer. And ESI is being incremented. So this is the thing that I was talking about, that what we're using to write with is being incremented. And then we come down here and we see that the value we're writing with is being used as a comparison to terminate the loop. So what's going on here is this loop is going to keep on receiving until it gets a new line. And it's writing it to EDI. If we trace up where EDI is coming from, EDI gets set here. This comes up from, this is being passed, this is an argument, it's a pointer. If we trace it back, this is where it's being passed. Just lost my place for a second. This is the stack buffer is part of the local stack for that function. It's the it's a local variable. I think it's like 800 bytes long or something. But so you're going to this function. You're passing a pointer to a stack variable. This is why you need to do inner function value tracking, because if we were only looking at that function, we wouldn't know if that was where that was coming from, if that was a certain size, or if it was being controlled somewhere else, or what it was about. That's why inner function value tracking is so important. So this is an exploitable vulnerability. It was a client-side attack. I don't know if this was reported to Trillion. They said that, I believe on this one, that they said that it was unlikely that someone would have a fake RSS server trying to exploit a client side. So it's been reported. I don't know if it's been fixed. You can go ahead and check your latest version of Trillion. Before I forget, let me... What's that? I don't think it really matters, right? They were told. You know, it's sometimes you tell vendor stuff, and if they don't want to fix it, they think it's not a problem. I don't know what to tell them. So this is the function, if you guys want to write down the address. I'd check, if you use Trillion, I would check it. So this is a simple vulnerability, and it was caught using binary static detection, and it catches bugs. Here's the something kind of similar. This is the MSRPC blaster. There was an overflow in the machine name. Basically, going into this function, all it wants to do is pull out the machine name. It knows that the machine name is terminated by backslash, so it's going to keep on writing into destination until it finds the backslash. So you can make that as big as you want, and you overflow a stack buffer. And I actually took this snippet from Mark Dowd's new book. It's an awesome book. If you don't have it, you should definitely check it out. Art of Software Security Assessment. There's all kinds of stuff in there for source code auditing, but a lot of it applies to binary auditing as well. It has really good sections on signed attacks, on integer. When things get stepped up to integer, comparisons between negatives and positives, comparing lots of comparison-based attacks on there, and they cover a lot of the vulnerabilities that they've discovered over the years, like the SSH challenge attack that one of them found. There's also the CRC32, the detach, the X2 bug. There's tons and tons of stuff on there. If you don't have that book, I would definitely get it. So bounded loops. Bounded loops means that there's some type of condition that's going to stop it. Whether it's, let's say you're saying go through this loop 10 times or whatever. Just because it's bounded doesn't mean it's not vulnerable. There's been lots of vulnerabilities with like inline WSN copy, where people think that function from Windows takes the number of bytes, but it takes the number of wide characters. So they put too many on there, and basically you create you can write twice as much to the output buffer as you intended. So the way that you look for this is you find that the closed loop, the jump back to the top. You look for pointers that are being written to and incremented. You see that there's a comparison with the input, and there's a variable, whether it's a register or on the stack or whatever it is, it's being incremented or decremented by a certain amount each time you go through the loop. So when you enter the loop and you're writing to this buffer, every time a buffer is created, we know the size of it. We register like all malloc calls, all the stack allocations and whatnot. We know how much space there is. So we just go through this and just double check. Make sure that you can't write more than the buffer allows. So that's really quick coverage of what it does and what we've done so far. Like I said, it's still a proof of concept. Right now, there's probably daily check-ins, daily changes. Been writing a lot of stuff for the emulator. I tried connecting earlier to pull down the latest build from SourceForge, and I had a problem with my internet. But if you catch me later, I'll have it on my laptop, and I can show you what's going on, or you can just pull it down yourself. So check it out. It's there. It's open source. You just look at the code. If you have any ideas, if you guys think I'm doing something wrong or something could be better, I would love the input. And is there any questions?
Keine Fragen?
Well, I guess I answered everyone's questions in the talk, huh?
Why did you choose to implement in C#? Sorry.
What's that?
Why did you choose to implement in C#?
I chose to implement in C# because Matt chose to implement in C#, and I was kind of forced to, I could say. But the real reason we did C# is because of mono, because we could run it in Linux. It was sandboxed. The other choices we had was like a scripting language like Python or Ruby, or and I don't know. I kind of didn't want to do that. Go ahead.
Another question. Did you run into any bugs that changed when you started to observe them?
Any bugs that changed?
Changed behavior. So you run the program like normal, it behaved differently than when you run it through your program.
Honestly, the code is so proof of concept that we're not at that level yet.
Okay, thank you.
Hi. I'm thinking about the stopping problem, and I was wondering if you've thought about how you're going to deal with things like recursion and possibly machine states that will not, where you will not reach, where you cannot easily determine whether you will reach a stopping state.
Yeah.
Things like that.
So yeah, there's definitely a halting problem, right? And what we're doing is basically a balance of kind of bang for buck. So we're saying, okay, we're going to reject these values because there's no way we can handle this many states, and we're going to miss stuff, right? That's just going to happen. I mean, it's either we do that and get some kind of results, or we try to come up with, you know, God's own static reverse engineering tool, and it'll never happen. So if there's no more questions, I do have some shameless self-promotion. Teaching 2 training classes. One's going to be at RSA in San Francisco, and the other one's going to be here in Amsterdam, in Europe, in March. So they're going to cover how we build these types of tools, what types of open source tools are available right now, what types of analysis you can do that, how you can extend it, and how to build a tool like this for yourself. And thank you, Congress. It's been a great time. This is my second time here, and I love it. Thank you.